In December 2024, a machine did something no computer in history had ever done. It got more accurate by getting bigger. Every processor you have ever touched, every laptop, every phone, every supercomputer buried under a mountain in Nevada breaks down as it scales up. More parts mean more failure points. But inside a lab at Google, a chip named Willow proved the opposite law. Add more qubits, and the errors did not pile up. They vanished. This is not a small technical footnote. This is a reversal of a rule that has governed every computer ever built since the first vacuum tube flickered to life. Classical machines have always obeyed a brutal, unchangeable logic. The bigger you build them, the more they fight themselves, heat rises. Noise creeps in, failure rates climb. Engineers have spent 70 years designing around this one unshakable fact because they had no choice. Quantum computers just broke it. Let that sink in for a second, because most people hear quantum computer and picture something abstract, something theoretical, a science fair project decades from mattering. That perception is now dangerously out of date. What happened with Willow is not a promise about the future. It is a measured, repeated, peer-reviewed result published in Nature, showing that a machine built from the strangest physics humans have ever discovered now scales in a direction no classical machine ever has. To understand why this matters, you have to understand the wall that has haunted computing since the very beginning. Classical. Computers are built from transistors, tiny switches flipping between 0 and 1, on and off. For decades, engineers packed more of these switches onto smaller chips, and performance climbed. This was Moore's law, the quiet engine behind every leap in consumer technology from the 1970s onward. But transistors do not scale forever without a cost. Pack too many into too small a space, and heat becomes an enemy you cannot design your way around. Modern processors already sit at the edge of that wall. Chips today generate so much heat per square millimeter that some engineers compare the density to a nuclear reactor core. Cooling systems, once an afterthought, are now half the engineering budget of a data center. And even with every trick available, physical error rates in classical logic gates do not improve as you add more components. They stay roughly fixed, or they get worse because more components mean more places for something to go wrong. Look at the history of processors sold to ordinary consumers. The pattern is impossible to miss. Clock speeds climbed steadily through the 1990s and early 2000s, then plateaued hard around the mid-2000s because pushing electrons faster through smaller wires simply generated more heat than any practical cooling system could remove. Engineers responded by adding more processing cores instead of faster ones. A workaround, not a solution, and workarounds have their own hard limits too. That plateau forced an entire industry to change strategy. Instead of making individual components faster, engineers focused on making systems wider, running more calculations in parallel, rather than pushing any single calculation to run quicker. It worked for a while, and it is the reason your phone has multiple processing cores today instead of one blazing fast one. But parallel scaling has its own ceiling, and that ceiling is exactly the same one classical error correction runs into. More components, more heat, more failure points, no escape. Quantum computers were expected to inherit this same curse, only worse. Qubits, the quantum equivalent of a transistor, are almost unbelievably fragile. A stray vibration, a microscopic temperature fluctuation, even a cosmic ray passing through the chip can collapse a qubit's delicate quantum state and destroy the calculation running on it. For years, this fragility was quantum computing. S' single greatest obstacle. Skeptics argued it might be a permanent one, an unsolvable flaw baked into the physics itself. Here is the number that should stop you. A single physical qubit today has an error rate hovering somewhere around 1 part in 1,000 for each operation performed on it. That sounds small until you realize a real computation needs millions, sometimes billions of operations chained together. Multiply a small error by that many steps, and the result is garbage almost instantly. This is why, for 2 decades, quantum computers were treated as fascinating but functionally useless outside a handful of narrow lab demonstrations. The fix researchers proposed decades ago was called quantum error correction, and on paper it looked elegant. Instead of trusting a single fragile qubit to hold information, you spread that same piece of information across many physical qubits, bundled together into what is called a logical qubit. If one physical qubit in the bundle flickers and fails, the others can detect the error and correct it, the way a group of witnesses can catch one person's lie by comparing stories. The theory behind this idea is called the threshold theorem, and it was proposed all the way back in the 1990s. It states that if the error rate of your individual physical qubits falls below a certain critical value, then adding more qubits to your error-correcting bundle does not just help, it exponentially suppresses the total error rate. Below that threshold, scale becomes your ally. Above it, scale becomes your executioner, because you are simply adding more ways for the system to fail. For nearly 30 years, this threshold was a mathematical prediction, not a demonstrated reality. Every lab that tried to build larger error-correcting qubit arrays found the same disappointing pattern. As they added qubits, the logical error rate stayed flat, or it got worse. The extra qubits meant to catch errors were introducing new errors of their own faster than they could fix the old ones. Scaling was not making these machines smarter. It was making them noisier, exactly like every classical machine before them. Then came Willow. Google's newest superconducting chip carries 105 physical qubits arranged in a grid, cooled to a temperature colder than deep space, roughly 1/100th of a degree above absolute zero. Researchers built a series of error-correcting grids on this chip, each one larger than the last, moving from a 3x3 arrangement of qubits up to 5x5 and finally 7x7. This growing structure is described using something called code distance, and it is the key number in the entire story. At a code distance of 3, the logical qubit performed roughly as expected from earlier experiments, fragile and error-prone. When researchers scaled up to code distance 5, something remarkable happened. The logical error rate did not stay flat. It dropped. Then they scaled again to code distance 7, using all 101 of the available qubits in that configuration. The error rate dropped again, and by almost exactly the same proportion as before. Picture the grid itself for a second, because the physical layout matters to why this result qubit in the array sits wired to its neighbors, connected by microwave control lines, threading down into a dilution refrigerator, the size of a small room. Every one of those connections has to be calibrated individually, tuned so precisely that a temperature drift of a few thousandths of a degree can throw off an entire run. Scaling this grid from 9 qubits to 25 to 49 is not simply a matter of adding more of the same part. It is closer to rebuilding a symphony orchestra from scratch every time you add new musicians, and expecting the music to get cleaner, not messier, with every new player added. The number researchers measured was a suppression factor of 2.14. Each time they increased the code distance by 2 steps, the logical error rate was cut by more than half. Not once, repeatedly, consistently, exponentially. This is the mathematical signature the threshold theorem predicted 30 years earlier, finally observed in a real, physical working machine. The final distance 7 memory achieved a logical error rate of just 0.143% per correction cycle, the lowest ever recorded on a quantum processor of this scale. Here is the detail that turns this from an interesting lab result into a historic milestone. That final logical qubit, built from 101 fragile physical qubits, was actually more reliable than any single one of the physical qubits used to build it. Researchers call this crossing beyond break-even, and Willow's logical memory outlasted its best individual physical qubit by a factor of 2.4. In plain language, the team built something out of unreliable parts that ended up more trustworthy than any single part inside it. Now compare that to what happens when you try the same trick with classical hardware. Add more transistors to a chip, and you do not get a more reliable computer. You get more heat, more power draw, and eventually more silent errors caused by thermal noise and voltage fluctuations. Classical redundancy schemes exist, and they help, but they do not create the same runaway positive spiral. There is no classical equivalent where doubling your components makes each individual component's mistakes matter less. Quantum error correction, once past this newly proven threshold, does exactly that. This is why researchers describe below threshold operation as the single most important unlock in quantum computing's entire history. It is not simply a performance improvement, it is a change in the direction of the curve. Every year before this, quantum computers scaled the same way classical ones do, getting messier as they grew. Now, for the first time, there is direct experimental proof that scaling a quantum machine in the right regime makes it cleaner, not messier, and the improvement compounds with every additional layer of qubits. Understand what compounding actually means here, because it is easy to skim past a phrase like exponential suppression without absorbing its weight. Linear improvement means doubling your effort gets you roughly double the benefit. Exponential improvement means each additional step multiplies your previous gain rather than simply adding to it. Willow's data shows error rates being cut by a consistent factor with each scaling step, which means the deeper you push this architecture, the faster your reliability compounds, not the slower. To put the scale of Willow's raw computational power into perspective, Google's team ran a benchmark calculation on the chip that took the machine roughly 5 minutes to complete. The same calculation, run on one of the fastest classical supercomputers currently operating on Earth, was estimated to take 10 septillion years. That is a 10 followed by 24 zeros. It is a time frame so far beyond the age of the universe that the comparison stops being useful as a number and starts being useful only as a warning. Skeptics are right to point out that this specific benchmark was chosen because it plays to quantum computing's strengths. And it does not yet translate into solving problems businesses or governments actually care about, like drug discovery or cryptography. That caution is fair, and any honest account of this story has to include it. Quantum computers with this level of error correction are still years away from outperforming classical machines on problems with real economic value. But the physics obstacle that many assumed would block that future permanently has just been demonstrated to be solvable. Google is not alone in this race, and understanding the competitive landscape makes the moment feel less like an isolated headline and more like the opening chapter of an industry-wide transformation. IBM has published its own roadmap toward fault-tolerant quantum computing, targeting a system called Quantum Starling for 2029, aiming to run 200 logical qubits capable of executing 100 million error-corrected operations. That is not a marketing promise. It is an engineering commitment from a company with decades of hardware credibility on the line. Other approaches are advancing in parallel, and they matter because they prove below-threshold scaling is not a fluke unique to Google's particular chip design. Researchers working with trapped ion and neutral atom quantum processors have published results showing similar resilience as their systems grow more complex. In some cases, seeing performance metrics improve rather than degrade compared to smaller, earlier versions of the same hardware. The pattern is repeating across multiple independently engineered physical platforms, which is exactly the kind of convergent evidence that turns a single surprising result into a validated scientific principle. Startups outside the giants are contributing to this convergence too, and their involvement matters because it shows this is not a story about one company's proprietary trick. Smaller, well-funded quantum firms working with entirely different qubit technologies, including nuclear spin qubits and photonic systems, have published results in late 2025 showing that key performance metrics held steady or even improved as their systems grew more complex, directly contradicting the old assumption that scaling always degrades quantum hardware. One research team specifically reported that any pair of qubits across separate registers on their processor could be entangled reliably, a capability that becomes dramatically harder, not easier, as systems grow unless the underlying physics genuinely supports scaling in the machine's favor. The research community's appetite for this problem has exploded alongside the results. A 2025 industry report tracking quantum error correction research found that the field published roughly 120 new peer-reviewed papers on the topic in just the first 10 months of the year, compared to only 36 papers across the entirety of the previous year. That is more than a threefold increase in a single year, a sign that the scientific community recognizes exactly what kind of turning point this is and is racing to build on it. But here is where the story gets genuinely uncomfortable and where it stops being purely a celebration of scientific progress. While quantum machines are proving they can scale in a direction that makes them more reliable, classical computing is running directly into the opposite wall, and that wall is not a metaphor. It is measured in real electricity, real heat, and real physical limits that no amount of clever engineering can fully escape. For most of computing history, shrinking transistors made chips faster, cheaper, and more power efficient all at the same time. That triple win is largely over. Transistors today are approaching sizes measured in a handful of atoms across. At that scale, quantum effects that quantum computers deliberately harness for computation start leaking into classical chips as unwanted noise, causing electrons to tunnel through barriers they are supposed to be blocked by. Engineers now fight the same strange physics that quantum computers exploit, except for classical chips, that physics is purely a liability. Data centers built to run today's largest classical computing workloads already consume electricity on a scale that rivals small countries. Some of the newest AI training facilities under construction are being built next to dedicated power plants because existing electrical grids cannot supply enough energy through conventional connections. This is not a future problem. It is happening in real time in multiple countries, as classical computing's appetite for power grows faster than the infrastructure built to feed it. Some of the largest technology companies on Earth have quietly become energy companies as a side effect of this problem, signing deals. 2. Reopen decommissioned nuclear plants and fund entirely new power generation projects, not because they want to be in the energy business, but because there is no other way to feed the classical hardware their businesses now depend on. That is not a hypothetical future scenario. Contracts like that have already been signed, and construction on some of these dedicated power facilities is already underway. Heat is the other half of this crisis, and it is arguably the more stubborn one. Every calculation a classical chip performs generates waste heat, and that heat has to go somewhere. As chips pack in more transistors to chase more performance, the heat generated per square millimeter climbs into territory that engineers openly compare to the surface conditions inside working nuclear reactors. Liquid cooling systems, once reserved for the most extreme supercomputers, are becoming standard equipment in ordinary data centers just to keep hardware from destroying itself. And even with all of that engineering effort poured into managing heat and power, classical error rates do not improve as systems scale. They do not compound in your favor the way quantum error correction has just been shown to. A larger classical system is not a more reliable classical system. It is simply a bigger version of the same fragile architecture, requiring more redundant hardware, more backup components, and more constant maintenance just to hold its failure rate roughly steady, not to improve it. This is the fundamental asymmetry now sitting in plain sight for anyone paying attention. One computing paradigm, the one that has powered every piece of modern technology for 70 years, hits diminishing and eventually negative returns as it scales. The other, the one many assumed was decades away from being useful, has just demonstrated the opposite behavior in a real, published, peer-reviewed experiment. Scale is now quietly separating two entirely different kinds of machines, sending them down completely different curves. Now, before this starts to sound like a countdown to quantum computers replacing your laptop, it is important to be precise about what has and has not actually been proven. Willow's below-threshold result validates a 30-year-old theoretical prediction about error correction, and it does so at a genuinely impressive scale. It does not mean quantum computers are ready for general-purpose use, and it does not mean classical computing is suddenly obsolete. Independent researchers tracking this field place below-threshold error correction technology at an early experimental readiness level, several major engineering steps away from the millions of logical qubits a truly transformative machine would require. The talent pipeline needed to build that future is also, honestly, alarmingly thin. Industry analysis published in 2025 estimated that only somewhere between 1,800 and 2,200 professionals worldwide currently specialize in quantum error correction, while projections suggest the field will need between 5,000 and 16,000 specialists by the year 2030 just to keep pace with demand. More than half of quantum-related job openings currently go unfilled, and the specialized training required to fill them can take up to a decade to complete. The physics has taken a leap. The workforce built to carry that physics forward has not caught up yet. Still, the direction of travel is now unmistakable, and that is what separates this moment from the decades of quantum computing hype that came before it. This is not another paper announcing a marginal improvement in a lab curiosity. This is the first hard experimental evidence that a specific, predicted, mathematically rigorous scaling law actually holds true in physical hardware, and that the law works in quantum computing's favor rather than against it. Google's own engineers describe this as the strongest evidence yet that a full-scale, fault-tolerant, genuinely useful quantum computer can eventually be built. Consider what this means for the industries quantum computing has always promised to transform. Drug discovery today relies on simulating molecular interactions, a task that scales so badly on classical computers that researchers are forced to approximate rather than calculate exactly, even for relatively simple molecules. A quantum computer that keeps getting more accurate as it grows, larger is, in principle, a machine built for exactly this kind of problem, one where the exact answer requires more computational resources than any classical machine could ever practically supply. Even relatively small molecules involved in modern medicine contain enough interacting electrons that an exact classical simulation becomes computationally impossible almost immediately, forcing chemists to rely on approximations that occasionally miss the exact interaction that determines whether a drug candidate works or fails in clinical trials. A quantum computer that becomes more accurate as it scales up is not just faster at this task in theory. It is, for the first time, a machine whose error behavior moves in the right direction for a problem that has always demanded exactness. Classical hardware simply cannot supply at any practical cost. Materials science faces a similar bottleneck. Discovering new superconductors, better. Batteries, or more efficient solar cells, requires modeling how electrons behave inside complex materials, a calculation that grows exponentially harder with every additional atom you add to the simulation. Classical computers hit a wall here almost immediately for anything beyond the simplest materials. A quantum computer, scaling in the newly demonstrated direction, is uniquely suited to a problem that is, by its very nature, quantum mechanical. Then there is cryptography, the area that tends to generate the most public anxiety around quantum computing, and for good reason. Much of the encryption protecting financial transactions, private communications, and government secrets today relies on mathematical problems that are extraordinarily hard for classical computers to solve, but theoretically much easier for a sufficiently powerful fault-tolerant quantum computer. This is precisely why below-threshold scaling matters so much beyond the physics community. It is a measurable step toward a machine that could eventually break encryption schemes the entire digital world currently depends on. Governments and security agencies are already treating this seriously, years ahead of the actual arrival of such a machine, because The transition to quantum-resistant encryption standards takes time, and encrypted data stolen today could theoretically be stored and decrypted later, once a capable enough quantum computer exists. This threat has a name in the security community: harvest now, decrypt later. And Willow's results are exactly the kind of milestone that moves that theoretical clock forward, even if only by a modest amount. None of this happens overnight, and it would be irresponsible to suggest otherwise. Building a quantum computer capable of breaking modern encryption or simulating complex drug molecules requires not hundreds but millions of physical qubits, organized into thousands of logical qubits, running with a kind of below-threshold reliability Willow has only just begun to demonstrate at a much smaller scale. The distance between a 101 qubit demonstration and a million qubit fault-tolerant machine is enormous, and every serious researcher in the field will tell you so without hesitation. But enormous is not the same as impossible. And impossible was the word skeptics were using about below-threshold error correction itself as recently as a few years ago. The gap between theory and demonstrated reality has now closed on this particular question. What remains is an engineering challenge, immense in scope but fundamentally different in character from a challenge rooted in unresolved physics. Engineering challenges get solved through sustained investment, iteration, and time. Unresolved physics questions can remain unsolved indefinitely. The shift from the second category into the first is the real headline hiding underneath all the technical detail. If you zoom out far enough, what you're actually watching is the emergence of two fundamentally different technological futures, running in parallel, following opposite mathematical rules. Classical computing, the technology that built the entire modern world, is approaching a ceiling defined by heat, power, and physical component limits that scaling no longer helps and may soon start to actively hurt. Quantum computing, once the more speculative and fragile of the two, has just demonstrated a scaling law that runs in exactly the opposite direction, rewarding growth instead of punishing it. This does not mean classical computers disappear. Your phone, your laptop, the servers running nearly every application you use today will remain classical machines for the foreseeable future, and quantum computers are not designed to replace them for everyday tasks. What changes is the ceiling on the hardest problems humanity has, the ones classical machines were never actually built to solve efficiently in the first place. Problems in chemistry, materials, cryptography, and complex optimization that scale exponentially with complexity. Before Willow, the honest answer to whether quantum computers could ever reliably tackle those problems was genuinely uncertain, hostage to an unproven 30-year-old theorem. After Willow, the uncertainty has narrowed. The physics works, the scaling law holds. What separates today's machines from tomorrow's transformative ones is now measured in qubits, funding, engineering time, and trained specialists, not an unresolved scientific doubt about whether the entire approach can even function as designed. If this kind of deep dive breakdown is something you want more of, hit like and subscribe, because this channel is going to keep tracking every major shift like this one as it happens, translated out of dense research papers and into something you can actually follow. Consider, too, how quietly this milestone arrived compared to how loudly it should have. There was no dramatic public unveiling, no keynote stage, no headline dominating every news cycle for a week. It was a peer-reviewed paper published in Nature, filled with technical language about code distances and logical error suppression factors, the kind of publication most people will never read directly. But strip away the technical language, and what is left is one of the most consequential experimental results computing has produced this decade, quietly rewriting an assumption that shaped 70 years of engineering. That mismatch between significance and visibility is worth sitting with for a moment. The most important shifts in technology rarely arrive with fanfare. They arrive as a number in a table, a graph with a downward sloping line where an upward sloping one was expected, buried inside a paper that only a few thousand specialists worldwide are fully equipped to evaluate. By the time the implications become obvious to everyone else, the foundational work has usually already been done, quietly years earlier. There is also a deeper, almost philosophical layer to this story that is easy to miss underneath all the technical specifics. For most of human history, and certainly for all of computing history, the assumption has been that complexity is the enemy of reliability. Bigger systems, more moving parts, more components interacting with each other. This has always meant more ways for something to break, more places for failure to hide, more risk accumulating with every added piece. That assumption is not just a rule of engineering. It has functioned almost as a law of nature. What Willow demonstrates, in a very narrow but very real sense, is that this assumption is not universal. It is a property of classical physics, of classical information, of the way ordinary bits behave when you wire enough of them together. Quantum information, it turns out, does not have to obey the same rule, provided you can get your error rates below that critical threshold first. Complexity, in this specific and carefully engineered context, becomes a source of strength rather than a source of fragility. That is a strange thing to sit with, because it cuts against nearly a century of hard-won engineering intuition. Every bridge, every building, every classical circuit humans have ever built follows the logic that more components mean more risk, managed carefully through redundancy, but never eliminated, never reversed into an advantage. Willow is one of the first pieces of concrete evidence that a different kind of system, built on different physical rules, can flip that logic on its head, using scale itself as the tool that suppresses the very errors scale would normally introduce. Whether or not you ever interact with a quantum computer directly in your lifetime, the ripple effects of this result are already spreading outward through the industries, racing to build on top of it. Pharmaceutical companies, materials researchers, national security agencies, and technology giants are all recalibrating their timelines based on results like this one, moving certain investments and research priorities forward. Because a theoretical wall many assumed would take decades longer to test has just been tested, and it did not hold. The honest, calibrated conclusion is this. Quantum computers have not replaced classical machines, and they will not for a long time, possibly not for a very long time in domains outside of highly specialized scientific computing. But the specific, narrow, and previously unproven claim that a quantum computer could get more reliable as it gets larger, the exact opposite of everything classical computing has ever demonstrated, is no longer a theory. It is a measured result, repeated across multiple scaling steps, published, reviewed, and now being chased by every serious quantum research lab on the planet. Somewhere in a cooled chamber colder than the vacuum of deep space, 101 fragile qubits worked together and became more trustworthy than any single one of them alone. That is not science fiction. That already happened, and the machines built on that principle are only going to get bigger from here, which, for the first time in computing history, is exactly the direction you would want them to grow.